So we'll discuss about semiconductor in this video. Conductivity of a semiconductor lies between that of a conductor and an insulator. So as the name suggests, it's a semiconductor, means it's half conductor. So conductivity wise, it is somewhere in between conductor and insulator. And if you want to verify the conductivities, so conductivity of conductor is 10 to the power 2 to 10 to the power 8 Siemens per meter. That of semiconductor is 10 to the power minus 6 to 10 to the power minus 5 Siemens per meter, and conductivity of an insulator is 10 to the power minus 11 to 10 to the power minus 19 Siemens per meter. So these are the values. Siemens is actually ohm inverse, and which is also called mho. The most common examples of a semiconductor include silicon. It's widely used in the manufacturing of electronic circuits and photovoltaic cells. Germanium, used in transistors and diodes, although less common than silicon. Gallium arsenide, used in high frequency and optoelectronic applications. Then we have cadmium selenide, employed in solar cells and light emitting diodes. So both silicon and germanium, they have a tetrahedral structure. For example, suppose this is the structure of silicon. So in this structure, you can say that one silicon is surrounded by 4 others. So it's a tetrahedral structure. Silicon has a tetrahedral structure known as diamond cubic lattice. Each silicon atom is covalently bonded to 4 neighbors in a 3D tetrahedral arrangement, and the bond angle is 109.5 degrees. At 0 Kelvin, all valence electrons are in their bonds. There are no free electrons. A semiconductor is a perfect insulator at 0 Kelvin. But as temperature increases, bonds break and electrons become free. When an electron leaves from a bond, there is a vacant space left in the bond, and that is called hole. Conduction occurs due to the motion of free electrons as well as a motion of bonded electrons in holes. When a bonded electron from position A fills up hole at position B, the hole moves from B to A. See, when a bonded electron moves to its neighboring hole, it remains still bonded, but at a new position now, and it leaves hole at its previous position. Now consider the amount of charge flown in the process. Minus E charge moves to the left like this, and if we assume plus E charge on the hole, that is, if we assume hole to be a positively charged particle having plus E charge, then consider the motion of hole. It moves plus E charge towards the right. And these two processes are bringing the same amount of charge across the line shown in the figure. This is the reason why holes are treated as having positive charge. So whenever we have to say that bonded electrons have moved from one atom to another, we talk about motion of holes in opposite direction. Just a convenient way of saying the same thing. One more thing, if we assume plus E charge on a hole, are we disturbing the total charge of the specimen? Because after all, hole is not carrying any charge. So where the heck it's obtaining the charge from? It is simply the charge of ion that the ion gets when its bonded electron leaves it. That charge is given to the hole rather than to the ion. So it doesn't make any difference, you see. So whenever hole moves, it carries positive charge, or you can say wherever hole goes, that ion carries a positive charge as its bonded electron has left from that particular atom. So is equivalently the same. We say that a positive charge is connected to the hole. So what we assume plus E charge on a hole. Instead of saying that a bonded electron has moved, we say that a hole has moved in opposite direction.